We're given an electrical circuit. We want to find y of t as t goes to infinity for this sinusoidal input. So since we're looking for the solution as t goes to infinity, we want the particular solution, which will have the same form as the forcing function. So y of t is going to look like some magnitude y sub m cosine of the same frequency, 3 radians per second times t, plus some phase angle theta sub y. And we need to find the magnitude and the phase angle, and then we know everything we need to know about this. Now to get this steady state solution or particular solution, we can just plug u of t and y of t into the differential equation governing the circuit and solve for y sub m and theta y. So first thing we need is the differential equation. When I'm writing the differential equation governing a circuit, I'll label voltages across capacitors and currents through inductors. The current through the inductor is already labeled as y of t. Then I'll take advantage of my voltage-current relationships. So the voltage across this inductor is going to be 2 henries times dy by dt. Now I've defined my voltages and currents, and I've got my passive sign convention taken care of. I just have to rely now on KVL, KCL, and Ohm's law. The 6 ohm resistor and the inductor are in parallel, so this voltage is also 2 dy by dt. Now if I define this as node A and do KCL there, V sub A, which is 2 dy dt minus u, divided by the 2 ohm resistance, plus the current through the 6 ohm resistor, which is 1 over 6 ohms times its voltage, which is 2 dy by dt, plus the current through the inductor, which is just y, sum up to 0. Now doing the math, I get this 2 cancels with that one, so dy dt plus 1/3 of dy dt is 4 over 3 dy by dt plus y. Then I have 1/2 u. If I take that to the other side, that's u over 2. Now I can just plug my sinusoids into this and solve for the values that I need. However, it's easier to work with complex exponentials. So let's pretend again that u of t is some phasor which has an amplitude of 2 and a phase angle of minus 30 degrees times e to the j 3t. If that's the case, then y of t is going to have the form of a phasor y e to the j 3t, and dy dt will be the phasor y times j3 times e to the j3t. Now I can plug these into my differential equation. So bringing this up here, 4 over 3 times dy dt, which is j3y as a phasor e to the j3t, plus y, which is just y e to the j3t, is equal to 1/2 times u, which is 2 e to the minus j 30 degrees, e to the j3t. The e to the j3t's all cancel out. Grouping terms and solving for y, the phasor, gives me, let's see, that cancels with that, e to the minus j 30 degrees over, that cancels with that, j4 plus 1. Division is more easily done in polar form for me, so this is e to the minus j 30 degrees over the magnitude is the square root of 4 squared plus 1 squared, which is square root of 17, e to the j inverse tangent of the imaginary part is 4, the real part's 1. So plugging the numbers into a calculator, I get this as being 1 over square root of 17 e to the minus j 106 degrees. So y of t becomes 1 over square root of 17 cosine of the frequency is 3 radians per second minus 106 degrees.